All right. So for another installment, we were in the middle of discussing the relations between. So this is where maybe the beginning of the lecture. And, so we were talking about maps to the Hilbert scheme, and maybe I'll remind by definition. So if I have a map, means this map. So if I have a map in the Hilbert scheme, then by map I now mean this is without singularities. So no singularities here. Then both by the definition of the Hilbert scheme and also by the actual construction, this is the same. So by definition, if I have a Hilbert scheme with moduli space, this parameterizes this moduli space is this moduli space here. This parameterizes zero-dimensional subschemes of C2 of length n. And also, so this is also the same data as a map from, so it's a projection you get from structure sheaf of C2, which is so these are we think of this as polynomials in this kind of quiver arrows x1 and x2 applied to 1. And so this subjects by the quiver maps to that space V. And that had this V, which is the structure sheaf of that subscheme. Right. And so now if I have a map to that, that means I have a flat, well, in algebraic geometry means I have a flat family over the corresponding C. In terms of quiver data, means I now have all these maps in sheaves over my C, but that so in quiver data it means it has to be stable at every point, and in terms of subscheme it means it has to be well an actual subscheme, but being a regular map. This means that that object has to be flat over C. Flat for a subscheme means it's a limit of every point. If I pick any point, then the fiber over any point, so fiber over C, fiber over C, so maybe projection, maybe call it maybe call this map pi. So pi inverse, maybe pi is not the best. So I have a pre-image, so fiber over C, I'll just write. Is the limit of nearby fiber. So means if I take my whole scheme as the closure of the scheme of generic point. And we discussed that this is not a closed condition, right? So this means you have a family of regular maps that converge to something with a singularity. And the easiest thing to convince yourself that this is indeed the case, like for example, we will be talking, for us the favorite curve C is just P1. They'll just draw P1, so maybe C is P1. And then on P1 we can use just automorphism. So on P1 we will be using automorphisms of P1 to, for example, for current localization. And so maybe if I have fixed points 0 and infinity, and I use automorphisms to scale. So if I just change coordinates, stretch the coordinate on P1, so that means I mean all my points going that way. And so in the limit, I will have this has to converge. So map that is constant outside of 0 in P1, because I mean the just takes the constant value, whatever it was taken at infinity. That constant is whatever it was, whatever that map was taken at infinity. And so then, so this clearly cannot be flat because it's the right. So this means for me, whole the geometry is gone to one point, and that point is not a limit of the generic point. And so now we've we already discussed how we're planning to deal with this. I just remind everybody is that so there are two there are many strategies to deal with it, and then one was we could talk about quasi maps to help C to N, and this obtained by relaxing the conditions. So this is they relax. So we had the condition that being a subscheme of this C2 bundle over C means you have the structure sheaf of my C cross C2 surjecting to the structure sheaf of my subscheme. And that was, so this map is surjective to allowing this map, so relax the surjectivity. Surjectivity of this map. And so what do? They relax it to the conditions. So maybe we will call the projection, the whole projection from the bundle to the base. Maybe we'll call this map pi. So then, when I talk about quasi maps, I talk about the push forward. So I have V, it's a vector bundle. On my curve C, so that vector bundle I identify with the push forward of some sheaf, some one-dimensional sheaf. So this will be no longer a structure sheaf of subscheme, will be some sheaf F. So I push forward. So what does it mean push forward? That means I only remember the coordinates in the I only remember the coordinates along my base and don't forget the fiber coordinates, but they still in this push forward, the fiber coordinates still act. So here I have my operators multiplication by x1 and x2. They act here. So these are the quiver maps. So the quiver maps are this is the map from. So okay, so these are the quiver maps and that go from V to itself. So okay. So what would you like? So this wants to be a vector bundle, and we would like these guys to, if I take the powers of these operators and I apply them to, so to speak, one, instead that's the image of my framing map. So this means they generate my V, except at finitely many max point. And now if I translate this back into the three-dimensional language, that is the same as saying so what does it mean? I have a sheaf which is a vector bundle on a curve. We have a sheaf on a curve that is a vector bundle if and only if it has no torsion, means it, or if and only if it has no zero-dimensional subsheaves. So this means this is if and only the first part, this being a vector bundle, this happens if and only if no zero-dimensional subsheaf in F. So this is this part. Maybe I'll move this part here, and then this part, the generation part, this part means if I denote this map by S, means previously this map S was surjective, but now it can have can fail to be surjective, but at least it happens at finitely many points, means the dimension of the co-kernel of that map S, that is 0. So it means, so instead of having a surjective map, we change the condition to this map may fail to be surjective, means but it can have co-kernel, but the kernel is zero-dimensional. On the other hand, the sheaf itself, that's pure one-dimensional. There's nothing zero-dimensional in the sheaf F. Okay, so these are so in general, if you study objects of the form, so if I have a structure sheaf of threefold, and then with the map S, so this is the general moduli space considered by Pandey. In this enumerative concept was first studied Thomas, but those in algebraic geometry people also looked at similar modular spaces before, but this is called the Pandey-Thomas space, and so this is, you have with a map S to some sheaf F such that these 2 points are satisfied. This means F has no zero-dimensional subsheaves. So if pure dimension 1, just write pure dimension 1. One, and the co-kernel of S that has dimension 0. So this is this. So in this instance, the quasi-map stability condition is just equal to Pandey-Thomas stability condition. But many other possibilities, in particular, we could. So if I study so this falls into the general category of things. So it belongs to the general category to, broadly speaking, Donaldson-Thomas count. And this study, they count stable, and an example is here. You put some conditions of that kind. Object could be, this whole thing. It's an object. It's an object in the derived in complexes of sheaves. Stable object in categories. Does look like. sheaves on threefolds. And what do they mean? They look like sheaves on threefolds. It means for threefolds we have the X I between two sheaves, maybe F1, F2, that is dual to X3 minus I, F2, F1. So I have to move this. I'm running out of space here. And then tensor. It doesn't have to be Calabi-Yau tensor canonical. I always quick to point out that you don't need this to be Calabi-Yau, and in fact, this particular object we consider here, it's not a Calabi-Yau, but it's one has to have some control over that K. So dual. So one has property. One has to have properties like that. Means, in particular, that would be saying that since the deformation of an object is x1, and so x1 is the deformations from an object to itself, some kind of object, whatever. Call it maybe G. This is deformations, and then x2 GG to the abstractions. And then, well, x0 is the automorphisms, and so we see that these are roughly dual, the way we want them to be, approximately dual, the way we want them to be. And so this is an example of this situation. Like one of them shifts on threefolds, another example. So real example, the original really shifts on threefolds, maybe. In particular, curves. So it means like one-dimensional shifts in threefolds. And then other things are like sheaves representations, maybe representations of quivers. Quivers, they talk about something two-dimensional. So quivers are like, you know, an example of a quiver, right, is this Hilbert scheme of points on the surface, which has two-dimensional, which has this, which is 3 is replaced by 2. But so if I take sheaves on that objects over a curve, so in sheaves over a curve. Right. So this is the kind of thing that we consider. This is the kind of thing we consider here. And those are more or less some kind of version of quasi-maps. So you have something. If you have something two-dimensional, you make a family of these two-dimensional objects, and you get something three-dimensional. Right. So maybe I'll rearrange my material here. Right. And so then maybe the first kind of really enumerative appearance of that data is well in this MNOP papers. We focused on really there the situation was just before this. This was before Pandey Thomas. This was really ideal sheets. Of course, in threefolds. And then this means since you have see of the threefold, now it surjects to the structures of that curve. But then this means this means means giving up on V being a vector bundle. So you can allow V to be a sheaf, and then you can say, well, that sheaf I would like to be generated by my quiver map, but it will be no longer line bundles. I'll have a singularity as an object on my curve C. This will have singularity. So this is, and then there are many in general, many other options. Tons of other options. For stability conditions. So we will maybe I'll say something now, and then I'll talk about the examples of what does it really kind of what the DT versus PT, what the objects look like. Maybe I'll talk about that in a second, but maybe I'll make since you may wonder what would be the difference between them, and so then so kind of expectation. So there's a general expectation. Expectation supported by many computations, by many theorems and computations that all stability conditions give equivalent counts. Equivalent in the sense there is some dictionary which is not too complicated, a dictionary that tells you what if I want to count in one stability condition, what would that equal in some other stability condition? So that's maybe from some larger, okay, this is from some larger point of view, maybe these are these are still different languages. Like if I now have a text in French, I have text in Italian, they're not the same text, but they're from the point of view of in the general scheme of things, they're very close. So so this is equivalent count, and this is so this is known for local curves. The local curves we discussed threefolds of the form. It means a bundle over a curve. Curves in cohomology. In K-theory, area of, I should say, active current research. And then also in cohomology, equivalent to Gromov-Witten counts of curves. And again, this is not for local curves. And this is the original conjectures of MNAP. That was about this equivalence to Gromov-Witten. That was original conjectures of this kind of MNAP stuff. That there's you can count curves in threefolds in different ways. You can do Gromov-Witten theory, and then you get the same result there. Okay, but then I should say here in K-theory, this question mark, precisely for the reasons that, so in principle you can there's a lot of study of K-theory of this kind of ground-within modular space. In principle, the objects to consider that are defined. You can take the virtual structure shift and so on and so forth. But this is the result is that it just exactly because I mean I personally don't know what to do with the loss of cell duality. Like a problem to me. So I don't know what to do there, and so this is you can yeah. So this is some separate thing. I have no idea. So in the cosmology itself, it's not so important. But when you compute in case here, the way we will be doing it in this course, and the way people do it is cell duality is used. Some feature of cell duality this is used all the time. And as we discussed last time, that if you start really letting your in ground-within situation when you're kind of your curve is free to vary in an uncontrollable way, then you lose that self duality. So I don't know what to do with that. Right. So maybe I'll come back to the Earth. And so what is this? What PT versus DT looks like for C1 instead of C2. So maybe easier. So if I have a subscheme in C1, maybe I will draw. So the reason is that in if I want to draw something, then in 3 dimensions we can draw it. We can draw fixed points pretty reasonably well, and we'll talk about them in a second. But in when you have a in dimensionless, and maybe we can draw an arbitrary subscheme of C, or maybe defined e.g. maybe defined by the equation x minus some variable a, whatever cubed, times x minus b, something like that. Means I have a point. Means I have a point at b and like a very kind of thing point at a. Then maybe we can draw as we put a box here and 3 boxes there. Right. So this means my total so altogether the dimension of, or maybe the rank of my O of my subscheme. Let me copy it here. This is 4. So it's a 4-dimensional space and has kind of 3 dimensions here and 1 dimension there. And this is, if I think of multiplication by x, multiplication by x minus a, it's a nilpotent operator in this space. This acts like that. So this is I'm really what I'm drawing Jordan blocks. Of the operator x. Operator multiplication by x has 2 Jordan blocks, one with eigenvalue b, one multiplied by a, and one of them is just an eigenvector, and another one is a Jordan block of size 3, right? So maybe I've maybe I said everything can be said about this example. And so now if I have a map, now if I have a constant map, now let's look at the constant map. So I'll consider map from P1 to this scheme, which is constant. So maybe from P1 to help C1, and I want 4 points, which is constant equal to that outside of 0 in P1. So what would that look like? And so then I've here I've drawn these pictures ahead of time here. And so vertically, we talk about maybe this is my what was previously x. Maybe I will call it x1, and then I have coordinate maybe x0. And then what's written here are the kind of the Jordan blocks of multiplication. This is multiplication by x0, and this is multiplication by x1. And so that would be kind of the PT chamber, means the x0 module generates free module. So the x0 maybe acts freely. What does it mean? You have a vector bundle. It means you have your coordinate multiplication by coordinates acts it's a free action. So this means all, well, in my affine chart, that would be all infinite size Jordan blocks. So maybe instead of maps from P1, let's take maps from C. C, this has coordinate x0, and this has coordinate x1. And so then this is, but it may not generate. It may not generate the section of x0 and x1 may not generate the whole sheaf. So this means I only generate this much. So from 1. So this is generated. This is the span of x0 to the I, x1 to the j applied to 1. And I can, in principle, so there could be some part of my sheaf which I failed to generate, and these are the singularity. So you can think of this as something contains my actual sheaf contains some negative powers of the variable x0 as a module. Right? Does it make sense? Okay. And then so this is one thing. So this would be here we this is maybe this is the co-kernel. That part is the co-kernel. Yes. The red part that has a co-kernel, but this has. And now in this would be the Dtpt type of picture, and here's the dt type of picture, where so this box here actually this is part of the deal too. So in the dt part of picture, the singularities come from, so now x0 need not act freely. So the singularities come from the torsion of multiplication of x0. These are the things that just really support the origin. But then, but the condition of this being an actual ideal shift means that if I look at this column here, maybe if I look at this column here, this generates everything. under the action of x naught, right? So this means I have some subscheme of my target, and it gets under the action of x naught. It can have x naught can kill things, so things can get smaller and smaller. So instead of them things being equal width, so here the things are all x1 multiplication by x naught doesn't kill anything, but here it does kill things, and so things get smaller and smaller. On the other hand, here there are some parts that we're missing, some part that extends in the kind of negative direction of x naught, and these are the right. So that's the difference. So now you may appreciate the, so now after the discussion, now in 3 dimension, things look exactly, so this would be, we will draw torus 6 point. Means what does it mean? What does it mean, torus 6 point? Torus 6 point means an action of a 3-dimensional torus that scales x multiplication by x naught, x1, and x2, and yet leaves the picture fixed. That means the whole space, somehow the space is triply graded, which means spaces, or whatever, my sheaf f is graded by z3 and degree. If I consider multiplication by x1, then the degree x1 is when the x naught is like 1, 0, 0. Degree x1 is 0, 1, 0. And degree x2 is 0, 0, 1. And so then similarly, our picture would be extending, would be infinite in the one. So it would be infinite in this direction. And what would it look like? I have this prepared here. So I've plotted 2 different views of the same picture. So this is the PT part. So you should imagine that our axes go like that. Maybe this is multiplication by x naught, x1, and x2, and this is the part. This is the co-kernel, which things which extend in the negative direction. That's the co-kernel of S. And that's the same thing rotated. So for you can see what would be. So this means the that then since there has to be. So this has to be multiplication. So you have to have maps. Kind of here. Here it's. You have multiplications by x1 and x2, and the fact that you have no torsion in x1 means it puts a certain monotonicity, like means this box here, like if I have this box here, that has to go here, and it has to go in there. So those 2 maps have to be maybe the way to say it is that the maps here, x naught multiplication by x naught is always injective, right? X naught has no kernel, so it means this maps multiplication by x naught is injective. Means the slices of this picture, they have to increase, right? I mean, you take slices and get bigger and bigger. Increase. We don't need this slightly misleading, right? And then here's the opposite situation. This is instead of having a kernel of S, we have a torsion of. Here we have that is x naught torsion. These are things that x naught multiplication by x naught will kill eventually. And then this is, and then here the slices in. By slices, I mean I slice in x naught direction. In x naught. Slices along. Not fixed. They decrease. They decrease because we have to start from something, and then we generate everything from that, and so that means to get things, I guess, smaller and smaller. So this kind of maybe should give you some kind of feeling as to how these things are happening. And then I already tried to give some advertisement to Henry's paper. So maybe if you want to, so this is for gets much more interesting. It's a lot more interesting. For if I take C2 and replace it by AD surface, and you can find see the paper I referenced last time, and that paper was you find that reference. So this is Henry's paper called quasi-maps and stable pairs. And it describes particularly the relations to Brian-Steinberg theory. Now Steinberg, I apologize that somehow I couldn't remember his name last time, just because we have two different Steinbergs already just discussed in this course, and this is the third Steinberg. This must be called like the Steinberg course, I think. So right. So this is right, and we're sorry, it was still on this topic. And so then, right, the moral of that. So when you take the moral of that, if you have some data which looks like like a quiver data, you can take sheaves over a curve with values in that. Some linear data is like a quiver data. You can take sheaves on curves with values in that data, and then you can impose different stability conditions. You have different pictures, and these are different in principle, different enumerative theories, but they all believed or can be shown to be equivalent. Now, one thing I want to say is that, so when we took, remember we took the threefold to be of the form a curve, direct product C2. Well, we could have taken, instead of a product, we could have taken a bundle, right? So for example, we can take a direct sum of two vector bundles, two line bundles over my curve. It's also threefold. What does it mean from the point of view of quasi-maps? What does it mean? It means like if we take like x multiplication by x1, so maybe I'll just write multiplication x1 would be meaning multiplication by x1 is now a section not of home from VV, but now x1 is a coordinate on, so x1 is a coordinate on L1. And so the coordinate on L1 is an element in the line bundle which is dual to L1. And so we can in principle take we can consider twist of the following kind, right? So the twist of the quiver data by things like this. And so this is an example of a general principle. Our X was sitting so this was sitting in some quotient stack of the form, there's some kind of pre-quotient. I couldn't invent a good name or number for that. And then we model out by group G, right? But then, so we could have a situation that we have a bigger group, G tilde act on that pre-quotient, in which G is a normal subgroup. And then there's a quotient, which is, kind of group of automorphisms. Like this is, for instance, this contains this, well, this more or less equal, right? This contains at least the automorphisms of C2, or maybe GL2. The introductory words, all right. Like, GL2 for field C2. Yeah, and GL2 just acts. GL2 just acts here on this C2. Okay. And so when we talk about, instead of, we talk about what's a quasi map. So we had P was a principal. So instead of, so what we can do, maybe I'll put that C, so instead of P, which was the principal, simple G bundle, which in our case was this bundle V, we can consider maybe called P hat, which is a principal G hat bundle. With given image in G. So what does it mean? We twist not by just the group by which we quotient, but we twist by a bigger group. But we fix the image in these in G automorphism bundles, or we can also integrate over that, right? So this is G out bundles is that. So when we take GL2, then we can in principle make an arbitrary rank 2 bundle over a curve. So that would be, so this would be, that will be an example of that. It's an example of that GL2 bundle. Okay. So that's, this says that the data is not, if I have a large group of automorphism, the data is not restricted to G bundles. We can have bundles which with tradition function in some bigger group. That's fine. And that's important in the general development of the theory. That would be important. Right. So so now we'll have to. So we've discussed the moduli spaces. Now we have to set up the enumerative counts. So that's what we. So actually, I kind of let me prepare for that a little bit. So remember, we had some notation like the proctor X for that quotient stack. And so now we finally want to go, counts of curves. And by curves, I already discussed. These are more or less quasi-maps with some stability condition. Since we want to count, we want some proper moduli space. Means well, we discussed the options, and the options seem to me that there are many different versions of quasi-maps, and they're all interesting, but they all more or less should be more or less equivalent. And so, but what would be so first would be what would be the what sort of answers that would be? So these are the counts. They should give us what? So this we would like. What we want is some kind of tensors in. Well, we would like to remember a notion of curve meeting some cycle or things like this. So this is with the condition that we would like to count curves that meet some particular cycle, or so that cycle is recorded by an element in covariant K theory of X, and it may be at many different points, and so this means tensor to some power. But we should also allow for the possibility that occasionally, and this will be discussed presently, we should also allow the possibility that sometimes we get, instead of taking values in X, we in fact take values in the K theory of the stack. So that's an also. So this would be the shape of the answer is a tensor like that. And then what would it mean that we will compute it? So to compute means to describe, to identify these tensors in terms of quantum groups. Right? So that means, so in principle, these are huge. So these are huge. So if I think of the K theory of the Hilbert scheme is like a Fock space, and then so here I have like a bunch of Fock spaces and a bunch of who knows what. So something very, very big, and of course I'm not gonna write down every single entry in that tensor. Just it will take me infinite amount of time. But I will say what this tensor is in terms of, or we will say what this tensor is in terms of quantum groups. So that says that's like sometimes, like with a particular tensor, it would be really like the R matrix. In some other but that would be the shape of the answer. Now, how do we get this tensor? So we have we have to talk about evaluation maps. So what's an evaluation map? I have my moduli space. We'll denote it quasi-maps for, so quasi-maps is, it says, from some curve. Now arrow means a quasi-map to X. Maybe call it F. And suppose I have some marked points here, P1, P2, P3, something like that. Maybe call it Pn. Then I can take a value of my map F at the corresponding point. So I can take, maybe here, let's take a triple. record the data f of p1, f of p2, etc. And where that data would like. So if I just have a quasi map to the Hilbert scheme, let's say so this means the particular moduli spaces we would like to consider are the stable quasi maps to X inside my quotient stack here. And so if I take the value at a given point, generically these PIs are distinct from base points, but at a particular given point there might as well be a base point. So I'm here, this evaluation map really goes to this stack to the power. And so this would be the easiest, this kind of the easiest count. But and then we'll have to deal with the we also would like to have an evaluation map to X for reasons that will, in particular, what we would like is maybe called evaluation map. So what we can more generally we can go to the data, which is so first of all, we discussed that we can have stable quasi-maps, but we can also twist them. Twisted means twisted as twisted is by automorphism, by the group of automorphisms. And so this means we have some bundle over the curve with the group's automorphism, and we can remember, in addition to remembering this evaluation point, we can remember the data, which is the curve itself. And then with that bundle, P out, so that's one piece of data. And then we would like the values at this point. So this is a point in some kind of stack of bundles. This is a stack over the stack of curves, pointed curves, cross and we would like this to be something like so this would be a data. We would like it to be something like people call it extended. I guess it's called extended. Maybe other words. Extended like K-theoretic homological field theory. And that refers to the fact that so extended means we have this data, the data of the twist, and the homological field theory thing corresponds to what it does, what this collection of tensors should do under when I take my curve and I degenerate it. So if I have take my curve and I degenerate it to something. We only have genus 2, and the rest of the genus degenerate to a nodal curve, and then the marked point somehow and then the bundle, also the bundle. You can take a bundle, and then it also has two different bundles. Right? So there is a boundary in that stack. There's a boundary divisor of the kind where your curve, instead of breaks into components. So maybe I'll look at stack of like nodal curves, and then that has a stratification by how many nodes I have in my curve, and so I want to go to the next strata, and I would like to know what that K-theory class does on that strata, and then one thing which we will see, one thing one sees very clearly is that if when I consider some kind of gluing here, I want some kind of gluing formula. Gluing here, and then and when we talk about node and talk about information theory, is that node has to be disjoint from. So this is kind of important from information theory viewpoint. There have to be. So this is a node of my curve, and when I talk about quasi-map from a nodal curve, node have to be disjoint from base points. Because otherwise all the hell breaks loose. So then so this means even if I want some kind of consistent theory of objects like this, then we need to have an evaluation map that goes not to the stack but to the space X itself. And for many reasons this is good, because K-theory of the space X itself is something finite dimensional, whereas it's opposed to K-theory of the stack, which is something whatever, something nice but infinite dimensional. And so we would like to have that evaluation map to the K-theory of to X itself. So that means, so how do we get evaluation map? So to get that's COVID brain. So to get an evaluation map to X, not to the quotient stack, we need a slightly different space. We need a resolution. We need a moduli space that resolves the following map. So inside my quasi maps, I have a locus, which maybe denote quasi maps non-singular. Non-singular means at this given point. So this is a f of my at p, f at p in X. So this is open set. And so that means here I do have my evaluation map that just goes to f of p. This is an X by construction. And so this I need so this I need like a rational map. So it means I have a map that defines an open set. Means I need to, what do I need to do? So it means I have to, more or less somehow blow up the space. And now in a space in a way that I'll explain in a second, blow up this this space to get space which is quasi maps, maybe I call relative at P. It's still an open set here. still an open embedding here, such that this is regular and proper. Right. Okay, so what does the moduli space, I'll explain what's the, I'm not going to explain the whole theory, but I'll explain why would you come up with the following, answer, is that, so suppose I have, what's the, so there's some family, quasi-maps. You can imagine it's one-dimensional family for the sake of this discussion, but it could be some, you can take some family. And then what does it mean? So if I have, I can think of this, if I have a family, means I have my curve. So this my curve C, I will draw it vertically. So this is curve C, which may also depend on some maybe that family parameterized by some time. Could be, we can imagine one-dimensional, and that curve may depend on time. It's okay. And so then in that family, if I have a point, means I have a section of that family. In this whole family, this whole thing maps, kind of maps to X, right? So this is my marked point, called P. So this means we have a section of that family, so marked point. And then I also have in that family, I also have base points, and so maybe I'll draw base points in red. And the idea is that some bet value at time, the base point. So this is fine. So maybe base points are disjoint from my something like that. So these are base points. And so this is for generically, generically I can evaluate at my P fine, but at some bad time, T equal to T bad, the bad moment of time, it actually happens that the base point got into my section P. And now, now what am I supposed to do? Well, in algebraic geometry, we have a universal way to deal with things we don't like. We just blow them up and blow up in the sense of algebraic geometry. And what does it mean? What does it mean here? So it's just really this point gets blown up. Or more generally, you do some kind of semi-stable reduction, but it means if you maybe take some kind of weighted blow-ups, base changes, etc. So this are kind of details, and then when you're done, what will you have? Means maybe I'll get rid of that, and actually I have to redraw this whole thing, so I don't know why I don't know why. It's not. Yeah, it wasn't helpful to copy it. Right. So this is. Let me put it back up there, maybe like that. And so we had, at least we'll have some point we're trying to blow up in and that would look like this. So I get new components. Maybe I'll just, so these are the components of the exceptional divisor. Maybe I'll draw them. Maybe I'll draw this differently. Maybe I'll draw. So I get the components, the exceptional divisor. I'll draw them straight, but I draw this line differently. This is T equal Tibet fiber. And then my marked points gotten away from the, so once you blow it up, then the marked points on this. The marked point gets away from the pursuit of the base points. So this is not so unlike what we mean ordinary two-dimensional field series. If I have some insertion at a point in the world sheet and I'd like to keep it away from other operators, when other operators approach or other some kind of defects approach, then my point starts going on a new bubble, which is thereby escaping things we don't like. So this means that this new fiber will look like kind of an old curve. So this was the old curve. And now at the point where I had the mark point, so there's a point where I had it previously, then I have a new, I'm gonna get new, in this instance, I'm gonna get two new bubbles. And they're attached at the point where this is the point, the previous location of my P. And then my point P escaped here. So sorry. This is the new home of P. And then these are the base points. So this, in other words, the moduli point in this relative moduli space is you have at every point where you try to consider evaluation map, you allow it to stick in like a sausage link, think of this sort of kind of accordion or sausage link. It only opens. Point is that this thing, since this is only opens like sausage links, not like cacti. Something, right? So it only opens like that, and then it opens just enough, so that the base points don't catch your. So it could be, right? Let's say for the sake of the argument, let's say one base point was actually in pursuit of your. So it doesn't have could be in a kind of a closer pursuit. So let's say it was tangent. So this guy's approach it with a kind of linear speed, and maybe there's also something which was. So I'll try something which was tangent here. So things like that. And so then it means if I do this, then I need two blow-ups to to separate the pursuit of my of the base point to this mark point. So this will look like that. Okay. And so and then, well, this, you can ask, well, this curve is I recall that this curve we considered that was somehow a curve given to us. Given to us, or we took it. I don't know, we either took it or somebody gave it to us. Anyway, this was given to us, not to, this was given to us fixed, in particular parameterized. Means we can consider it in moduli, but right now we are on some moduli space of that curve. And then these new components are just P1s, and you can ask, well, P1s have automorphisms. And so this means this data, and you can say, you know, what do we do with these automorphisms? And then the answer is that we should really consider up to, so we consider a new curve as automorphisms, which is what? So it means you have a kind of sausage link, and I have one mark point. So this part is parameterized. And then the sausage link opens, I have one mark point. And at every part of that sausage link, I have two mark points. It's either a node or mark point. And so the automorphisms, which is isomorphic to C star times the number of bubbles. And we consider this data up to this. Up to this group of automorphisms. Previously, we didn't have any automorphism in the data. Our curve was given to us. It might have, we could have had some automorphism of the main curve, but we consider the action of this automorphism. We not mod out. But here we really mod, you know, by this we mod out by. Don't take any kind of mod out by this. So in particular, this when you mod something out, you should impose stability conditions, and so the new stability is modified, and that this was the old stability means the base locus, so the dimension of the base locus. That is 0, and the dimension of the stabilizer is 0. It's the usual familiar. That's the familiar condition from moduli space of curves. That if I wanted pointed curve, a good stability condition for that, the automorphisms of that be finite. So it means the stabilizer of that as a map has to be 0 dimension. But just prevents, in particular, this prevents unnecessary blowups. Unnecessary bubbles, like the kind of bubble. When you blow up extra time, what you're gonna get? You're gonna get like a I mean, if you blow up one time you don't need, then you're gonna get a constant map with no singularities and your marked point that has automorphisms. So that's we don't want that. But the point I want to make about this is that so note that this relative moduli state is a dilemma of the set. And in particular, when we take localization of that, this will look much more complicated. So like localization. Is complicated. Means a lot of things you don't want to somehow compute something about localization on industrial scale, but if you want to kind of first get into the subject and maybe test some conjectures and so on and so forth, then localization is a wonderful tool. And in fact, I want to make this advertisement today at 1. There will be a talk by Henry. So I keep making advertisements for Henry. So there'll be a talk by Henry. I should not forget my other students, so I should give equal attention to all of them. But today happens to be that Henry will be giving a talk about how to use his code for localization computation, which I encourage everybody to listen to that. And so this is right. When we get to M theory, I'll talk about Yasha's work and go into through all the students in order. Anyway, so this is localization. In this situation is complicated because this would be like, for example, e.g. even in the nicest cases, like the fixed loci. When the fixed loci, we had this previous boxes and stuff, and so in particular, fixed loci are not isolated. And I should have prepared. So when I print the notes, I put a picture, but I didn't prepare picture now. I should have prepared the picture. There's a picture of what the fixed loci might look like, and they're not there. And I'll put it in the notes when you can check it later. So now with this, maybe I'll conclude about the gluing and degeneration. We wanted this K-theoretic homological field theory, and then so this is the first thing is what should be quasi-map from another curve. So I have a quasi-map from a nodal curve. What does that thing should look like? And as I said before, that it's best if you don't allow singularities at the nodes, because then it gets really, I mean, from my point of view, is unmanageable at best. I would say don't do that. And so the usual condition is that nodes want to be disjoint with base points. We would like this thing to be empty. Well, how are we going to keep nodes away from base points? Well, we just had this discussion. So if I have my curve, maybe my curve, and I have nodes, sorry, base points. What would happen if base points will try to approach node? We just had the discussion how to deal with that, and then this means that you should allow yourself a situation where when your what was previously a node now opens into like an accordion of new P1s, and the base points can go on these accordions. Things like that. Right? And I remind you that this is up to here. This accordion is up to the action. Maybe module out, not up to means you mod out by the action. In this case of C3. C star cube. Right? And so that's just the definition. It means quasi maps from a nodal curve. They allow this. This means your curve will also kind of an accordion open at every node, and just accommodate to swallow. It will open this kind of this accordion to swallow the right accordion swallows. And then what we want is some kind of some sort of gluing formula for. So we would like to be able to compute the quasi-maps from another curve in terms of the quasi-maps from two parts. And so that means we have to compare. So we would like to compare. So versus. So if I normalization, take normalization, here I have I take one point and then another point, and they would be identified. And then what would be the result then? So this would be since it's a marked point, so maybe call it P1, P2, and we would like them to be identified. Means you have to put the condition that they go to the same point. Well, what would that look like? So this means we can have a separate coordinate on P1. And another coordinate on P2. And so if we just glue them, so what does it mean? So just glue just means pair with diagonal in X square where the points. So we have some evaluation of these 2 points, and what means we want to glue them means we pair it with diagonal where this point is pair of P1, P2 lies. It just means they go to the same point. This would be this glue, that would be, of course, this will give an overcounting. This gives. Right, because I mean, if you, it's clear. It's just I don't know. Of course, we will have to talk about K-theory classes and stuff, but just in terms of the data, this means if I want to take the coordinate before, I have to cut it somewhere, and to get, so I have to get from the coordinate to this kind of 2/2 coordinate, I have to cut it somewhere. So I have to make some extra choice, and if I just glue the 2/2 coordinates, it means I'll be overcounting geometric objects. And the reason and the way to deal with this is a general thing, is that instead of we don't pair with the diagonal, we pair with the so I'll just state the answer. You can think about it and I'll read about it. So this is explained at length in many places, but in particular you can read about it in, I mean, the style closest to what I'm pursuing here would be in my Park City lectures. That would be, you can read about there. So just the correct answer that if I want this kind of thing, then I have to take, so this quasi maps from this. This is, so diagonal means like a quadratic form on K theory of X, right? I mean, just an element in Kx squared. Maybe the dual of that would be like a quadratic form. And I have to pair not with diagonal, but instead I have to pair. So I take my denormalization. So now I have 2 mark points, P1, P2. So I have some elements. So this sits in this, the corresponding count sits in like Kx tensor square tensor whatever else I had before. So I have this kind of 2 indices sits in here, and I have to pair it with the right thing. So maybe I'll just denote it with the inverse of the form of the right quadratic form. It's like the inverse of that. It's called the glue matrix, and where the glue is a matrix which is just where it gets the just counts the coordinates. So this is, so this is like generalization of diagonal. So this starts out diagonal. This starts out. So if you have no coordinates, then it means I have the diagonal. So this is diagonal plus corrections. And this is in, so this is an element in k of x square. And this coordinates, I remind you, this would be here. This is modulo in this case 1, 2, 3, 4, 5, C5. This kind of thing. So I get some count, I get some tensor, in the square of a vector space, and if I take this is like a quadratic form, so that's inverse. This is in the dual. So if I have a quadratic form in a space, then the corresponding quadratic form in the dual space, if you take a matrix, like it's inverse. So which is why the inverse here. And so this is, and you pair this. So now these two objects you can pair, and then this is the right answer. Well, okay. So I'm out of time today, but particularly today I was trying to finish on time because I hope many of you will get a short rest and then listen to Henry's lecture. So that's all I want to say today. How about questions?
Could you please go to examples of Dtpt diagrams? Like,
sure. Three-dimensional, two-dimensional.
let us start from two-dimensional.
Okay.
Actually, like you have this example, like before you wrote that you consider x minus a cube, x minus b, right?
Yes.
Yes, and then you wrote this diagram. Is this diagram correspond to this example?
Yes, of course. This is the vertical thing. Is I have in the vertical direction. I have 3 boxes and the 1 box means a Jordan block of size 3 and a Jordan block of size 1.
Mm-hmm. And actually, maybe I don't understand. Like, why do you have so many boxes to the right? Are they infinitely many, or this finite number?
They infinitely many, yes. Because if I now if I consider maps there, that is like now it's a module over the coordinate x naught.
Mm-hmm.
And if I have a vector bundle, means this is a free module, so it has infinitely many.
Mm-hmm.
Right? So maybe I should put dots here.
Okay, so there are infinitely many green, but
Yes.
finitely many red ones, right?
Correct.
Okay. Well, and the same happens. Could you now show the three-dimensional picture? Like, what's about the dots in this picture?
This again goes infinitely in this direction. So this is maybe someone it's infinite.
Mm-hmm.
In this direction.
Okay, thank you.
Sure.
Can you say one more time where does this overcounting comes from? So you said when you just, because like usually you just can separate things into.
No, you can't, because there's no like, how would you, what's a canonical place to separate this picture? There's no canonical place, right?
Oh, I see, because you but for example, let's say, so if you have you might have like arbitrary number of this like p1s or whatever in the middle, so you just take the closest one to one of the parts.
To which part? So in the middle we have no marked points, right? So
I see. Yeah. Okay. I see.
Okay.
Yeah.
More questions? All right. Last call for questions. And well, I thank everybody for asking questions, because I think participation is great. Eventually, I think we'll be, hopefully this is right. Anyway, so this is all for today, and I to be continued next week, and so then.